Hello, I'm Dr. Patamaporn Sripadungtham. I'm a lecturer at the Department of Electrical Engineering, Kasetsart University in Bangkok, Thailand. Okay. Well, the series of lectures that you are going to follow or listening to now are the topics covered in a course called Circuit Analysis 1, which is an introduction course for our second year electrical engineering students. Okay. The materials are general basic concepts, not so difficult, but you need to have some knowledge in calculus and differential equations. Okay. I will make the lectures very simple throughout the semester, but you need to find on your own some examples from textbooks to do exercises, okay, so that you can pass the course. Well, the first topic for the lectures for this course, which I'm going to do right now, is on the definitions of all the electrical terms that you need to sort of like remember and know, okay, what they are. Okay, so today, okay, if you can see, I hope you can see the what's on the screen. Okay, well, chapter 1, I would say is chapter 1. Okay, what we're going to do today is, of course, on the review. If you know of this already, I'm very happy for you. Okay, I will do the units. Okay, review the units. Electrical fundamentals, what is electrical charge, the voltage, what kind of source of voltage it is, current, resistance, conductance, grounding, what is the basic circuit, what kind of sources we have, what is the definition of energy and power, okay, and what is power in electrical circuit. Okay, so this is what I will cover for this first lecture. Okay. So first of all, welcome if you are an electrical engineering student. You are you look around you, you know that things around you involve things with electricity. Okay, even if you and the area in electrical engineering diverse in many ways. You can go into electrical machines, electromagnetics, digital logic circuits, solid state electronics, electrical power systems, computer systems, instrumentation, communication system, control system, optics, electro-optics, and many more that has been developing in recent years. Okay, if you simply look at your car nowadays, beside this or the electric power car, okay, the inside of the car, okay, you can say airbags, your belt, your memory seat, your security, your the control system, your sensors, parking sensors, power steering, ignition, cruise, cooling fans, or the navigations or the entertainment that you have now, cell phone, Bluetooth, DVD, all involve us, the electrical engineering students, engineers. Okay, so be proud that you are studying this this so-called field. Okay, so let's get into our topics. Okay, so first the units. Okay, the units. Well, the units, it's best also that if you write it down, okay, as you sort of follow through my PowerPoint here. Okay, the system that we use, okay, is a standard international system, okay, of SI unit right here. Okay, so what do we have? So first one, the capacitance. Okay, these are the symbol, the unit, and you have a symbol that you have to remember, and you will remember eventually. Okay, capacitance is C. Okay, and unit is farad, F. Okay, charge, you can have a capital Q or a small q. Okay, the unit is coulombs, and the symbol for the unit is C. Okay, so you have to look at the context. Okay, whether it's C as a capacitance or C as a unit of the coulombs. Okay, conductance, capital G, and the unit is Siemens. Okay, the symbol is S. Current, of course, I hope that you know by now. Okay, it's I, could be capital I or small I. Okay, or small I, and unit is ampere. Okay, capital A. Energy. Okay, certain book use W, and certain another one use E as energy, and unit is joules. J as a symbol of joules. Frequency, small f, okay, small f, and unit is hertz. Okay, the way I like to write it is that hertz is capital H and a small z, okay, or z, okay, hertz. Impedance, okay, capital Z, okay, z, on unit is ohm, okay, and the symbol is omega. Okay, inductance is L, capital L, and unit of inductance is Henry. Okay, capital H for Henry. Power, okay, capital P, could be a small p too. Okay, and the unit is watt. Okay, and W. Resistance, okay, up to now I hope that you know that resistance stands for R. Okay, R stands for resistance, and unit is ohms, and the symbol is omega. Okay, reactance, we would learn this later when we do AC signal. Okay, reactance X, okay, unit is ohm. Okay, omega is the symbol of ohm. Time, okay, time small t, and unit is second. Okay, small s, and voltage, okay, V, capital V or small v, okay, and the unit is volt. Okay, capital V. Well, the flux density, magnetic flux, and magnetic force, okay, it's not really used a lot in this course, so I'm going to skip that. Okay, if you go to electromagnetic field, the courses, you will see a lot of these names and symbols. Okay, so right now, next one that you have to keep in mind, we have prefixes. Okay, it's something that tell you the power of 10. Okay, for the units. So first one, yotta. The symbol is capital Y, and the value is 10 to the power of 24. Okay, zeta, capital Z, or Z. Okay, it's 10 to the 21. Okay, exa, capital X. Okay, the power of 10 is 10 to the 18. 10 to 18. Peta, okay, peta is capital P. Okay, and it's 10 to the 15. Okay, Terra, we seem to be in the world of Terra right now because all the so-called our drive is now in terabyte. Okay, so capital T, 10 to the 12. Giga, okay, giga, I learned it as giga, okay, but of course you may have heard giga. Okay, jig, okay, so capital G, 10 to the 9. Mega, okay, so capital M, 10 to the 6. Okay, like mega mall, for example. Kilo, okay, kilo, small k please, small k. Kilo, 10 to the 3. Okay, milli, small m please, small m. Okay, small m, not capital M. Okay, small m. Okay, 10 to the minus 3, right? Millimeters, for example. Milligrams. Okay, micro, okay, mu is a symbol, and it's 10 to minus 6. Okay, nano, okay, small n, 10 to the minus 9. Pico, small p, 10 to the minus 12. Femto, okay, 10 to the minus 15. Okay, and atto, okay, A, 10 to the minus 18. Zepto, okay, Z, 10 to the minus 21. And yocto, it should be a small z and small a and small f. Okay, yocto, y, 10 to the minus 24. Okay, so these are the prefixes you put in front of your unit, okay, to tell you what the value is. Okay, so for example, if I said 10 microfarad, right, it would be 10 times 10 to the minus 6 farad, okay, or 6 kilo ohms, okay, it would be 6 times 10 to the 3 ohms. So this would be the way we use our prefixes with our unit. Okay, so now let's look at how we convert this unit. Okay, so the first question is, what is, if I want to change 5,400 microvolt into the unit of millivolt? Okay, the way we can do this simply is, of course, the 5,400 microvolt, we can write it as 5,000, right, 5,400.0 times 10 to the minus 6, correct, right? Now, I want to change it into something, we have to fill out, times 10 to the minus 3 volt, because milli is 10 to the minus 3, okay? So, to do this, okay, so you look at your the power of 10 first, from minus 6, okay, and if you want to change it to minus 3, you have to add 3, right, plus 3. So if you have to increase this by 3 order, the order of 3, right, we have to reduce the value of your values by the order of 3 also, right? So therefore, to reduce from 5,000 to a smaller number, we shift our point to the left 3 position, 1, 2, 3. So your decimal point would be here, so therefore the answer would be 5.4 millivolt. Okay, so this is how you can do it, and if you practice a lot, you can do it really fast. Okay, so this is how you convert the so-called unit. Or this one right here, if you want to convert this here 0.00022 microfarad, right, into something, okay, into picofarad. So therefore, I'm going to write that as 0.00022 times 10 to the minus 6 farad, and I want to change it to something times 10 to the minus 12 farad, like this, right? So therefore, if I look at the power of 10, if I want to change from minus 6 into minus 12, right, minus 6, I have to subtract minus 6 to get minus 12. So I reduce my order by minus 6. So therefore, for the values, I have to increase it in by 6 order also. So therefore, my decimal point would increase the value by moving to the right, the point to the right, 6 order, 6 positions, 1, 2, 3, 4, 5, and 6. So there's another 0 here, right? So therefore, it becomes 220 picofarad. So that's how we can do it, like sort of like a baby way, but if you do it often enough, it will come, naturally. Okay. So next one, okay, let's talk about our world of electricity, simply. Okay. Well, we all know that we have learned, okay, basically we have learned from chemistry, from high school, that everything in the world, okay, consists of a smallest particles, okay. There's molecules, okay, and molecule also divided into something smaller that we call atoms, okay, and atom would consist of what? It consists of nucleus, right? Nucleus in the middle, right? And we have some electron orbiting around that nucleus. And the nucleus consists of proton, right, in the nucleus, and neutron. and we learned that okay, proton would have positive charge, electron has negative charge, and neutron has no charge, right? That's what we have learned basic in science in high school. Okay, well, the electrons stay in a shell. Okay, stay in a shell. Okay, but whenever the electron receives some kind of force, okay, it can be enough. The enough energy of that force can sort of kick out electron out of its orbit or the bonding, and this electron become what is called the free electrons. Become free electrons. Okay, and if these free electrons, there's a lot of them move around, okay, it would result in current moving into certain directions. It would result in currents. Okay, also the number of free electrons can classify materials into three types. Cool. Three types. One is the conductor. Okay, conductor materials. Okay, conductor materials are the materials that have a large number of free electrons. Okay, and therefore hence allow currents to flow easily. Okay, copper is an example, so it's called conductors. Okay, insulator, another type is insulator. Okay, insulator has a very low number of free electrons. Okay, so therefore not many electrons will flow, and so there's no current flows. Okay, so therefore we use insulator as to prevent the flow of electrons. So for example, glass is an example of an insulator. Another type is semiconductor. Okay, semiconductor is like a name saying it. It's a conductor. It's semi, half, maybe, So semiconductor only carries current when certain condition is met. So example is silicon, germanium. That's a common semiconductor materials. Okay, so these are the three types. The semiconductors you learn more when you go on a third years, about in electronics field, or solid states electronics. Okay, so now let's go. Now next, let's do some definitions of basic terms in electrical engineering field. So the first one is electric charge, Q. Okay, well, electric charge is just an electrical property of atomic particles. Okay, so proton, as I said before, exhibits positive charge. Okay, whereas electron is negatively charged. Okay, well, if an object has equal number of electrons and proton, it's called the uncharged or neutral. Okay, but if an object has excess number of electrons, then we call that it's negatively charged. Or if the object has deficiency of electron, we say it's positively charged object. Okay, well, electric charge is measured in coulombs, and the magnitude of charge is 1.602 times 10 to the minus 19 coulombs. Please remember that. I mean, well, try to, since you're going to be electrical engineering, maybe you have to get this number into your head. Oh, Q is equal to 1.602 times 10 to the minus 19 coulombs. Okay, so therefore electron having a negatively charged would be written as minus 1.602 times 10 to the minus 19 coulombs, and whereas proton will be positive. Okay, also a negative charge, 1 coulomb would consist of 6 times 10 to the 18 electrons. Okay, just for you to know. Okay, so try to imagine, wow, if you have this much electrons, 6 times 10 to the 18, electrons, that's 1 coulombs. Okay, of electrons minus 1 coulombs. Okay, so this is the formula for charge Q. Okay, next term, voltage. Okay, well, we have said the voltage. Well, voltage is potential difference. Okay, unit is volt. Okay, for me, I always try to think, well, what is it then? What is a voltage? Okay, the way I try to explain to my student is that to you, okay, is that, well, let's say that if you have an object, okay, you have a box or something on a table, and you want to move that box, okay, from point A to point B, point A to point B. Okay, what do you have to do? Okay, I always ask my students that. Well, you have to push it, right? Well, one of the ways, push it, right? So you push it from the box from point A to point B. Well, that means you have to exert some kind of pressure or force, correct? So similarly, okay, in case of in the electric field, if you want to move like particles or electrons, for example, okay, from one place to another place, from A to B, well, we do the same thing, right? We have to have something to push it, okay, for electron from point A to point B. So that so-called pressure or force is this voltage, okay? So therefore, so electrical pressure to move charge over a given distance is the voltage, okay? Or the voltage is the driving force in electric circuit, okay? And we can express it in terms of this unit. Voltage equal to work per charge, okay? So if you write it as in terms of the unit itself, it's 1 volt. Simply 1 volt is equal to 1 joules, okay? 1 joules divided by 1 coulombs, okay? 1 joule by coulomb. So if you say 1 volt, 1 volt, what is it? What is it 1 volt? Okay? So 1 volt, the definition is a potential difference, okay, between 2 points when 1 joules of energy, like 1 joule, see, 1 joules of energy is used to move 1 coulombs of charge from one point to another point. Okay, so therefore, VAB, if you say VAB, that can be thought of the work done by the electrical system in moving charge Q from point A to point B. Okay, so this is the voltage. Okay. Right, so now, of course, the voltage can be positive or negative. Another definition, so another word that we call voltage is potential difference. So for example, if you have a box, something, okay, right? This is how we write potential difference. Okay, so the potential difference between point A and point B, and we call this VAB. For me, I was always think of it, if I say VAB, I would take A as positive and B as a negative terminal. Okay, there must be a difference. Okay, the potential at A is higher than the potential at point B. Okay, so also voltage can have the value of positive and negative values. Okay, so therefore in this picture it explains that, well, if you have VAB, right, VAB equal to 5 volt, okay, we can also write it as VBA is equal to minus 5 volt, same thing. Okay, was it the same thing? So for example, if I say, well, if I said VBA is equal to 5 volt, if I write it as diagram, right, it would be, this would be B, right, this would be A, and this VBA, minus 5 equal to minus 5 volt, right? So it means that if I flipped it, okay, this is A, this is B, plus minus, right, VAB, it would be equal to 5 volt. I just flip the terminal, right? This is plus and minus. Minus 5, it means that if I flipped it to AB, the value will be plus 5. Okay, so therefore these two are the same. Okay, and we conclude that VAB is equal to minus VBA, like this. Okay, so for the voltage or potential difference, okay, point A to point B. Okay, well, the source of voltage, okay, could be, well, we can convert chemical energy to electrical energy. For example, is the battery. Okay, we can convert mechanical energy into electrical energy, the generator. Okay, and we can convert sunlight energy into electrical energy, which is solar cells, for example. Okay, so there are right now there are many research, okay, trying to use natural sources, okay, to convert into energy into electrical energy. Okay, so next one, current. Okay, current, the symbol is I, or capital I or small I. Okay, unit is amperes. Okay, well, what causes current? Okay, current, you can imagine that, okay, now that I have electrons, right? Electrons can move because I have the voltage, okay, to push it in certain directions. Okay, so as the electron moves, so in this picture, right, let's say if I write it like this, right, there's a cross-section area like this, okay, right, and this group of electron moves through this cross-sectional area, okay, we can imagine that, oh, okay, then we have current. Electrons moves, we can say that we can know it by measuring the current, I. Okay, well, in this lectures, this course, okay, we define the direction of current, okay, opposite to the direction of the electron movement. Okay, so if these electrons, okay, move these directions, electron moves in this direction, okay, right, then we say that our current move in the opposite direction like this. Okay, so there is some book, okay, when you buy your textbook, if you will ever buy a textbook, okay, you have to be careful that sometimes the book would say that electron flow version. Electron flow version. If you have this written on the cover of the book, it means that in that book, okay, the current direction is the same as the direction of the electron movement. Okay, so but for us, we don't use these versions. Okay, so therefore this is current. Okay, current also can be written, since it has directions, it can be written in positive and negative values. So therefore, okay, if I say that I have a current I equal to 3 amps moving into, from left to right directions, okay, I can also say that it's equivalent to, if I say that, well, I have I equal to minus 3 amp, but moving in the opposite directions. Okay, so these two are equivalents. Okay, so you have to be careful in problems. Okay, in an exam, for example, if you have assigned that please find the current in these certain directions, you have to give me the correct values with that direction that I have given in the problem. Okay, so, well, the definition of, since it's a movement of charges, right, electrons, so therefore the definition, the formula or definition of a current I is equal to dq dt. Okay, or if you look at the way this is written in terms of the unit, 1 amps could mean, 1 amps can be interpreted as, well, I have 1 coulombs, amount of 1 coulombs of charges, okay, passing through a given cross sections in 1 second. 1 second. So that's 1 amperes. Okay. So here, if it's written in a proper form, 1 ampere is the amount of current that exists when a number of electrons having a total charge of 1 coulombs, or these values, okay, 8.24 times 10 to the 18 charge carriers, move through a given cross-sectional area in 1 second. Okay, as we're looking at as the introduction course, so it's movement electrons. If you go into solid state electronics, okay, you know that, well, there are also movement current can be, formed from the movement of holes, which is a positive charged particles. Okay, so therefore, but right now in this class, just take that it's a movement of electron that causes current. Okay, that result in current. Okay, now currents, okay, can be sort of like divided into 2 major types, which is the direct current, DC, okay, DC direct current, which is a signal that is independent of frequency. And we always see is that, well, it's a straight line all the way, doesn't change with times, okay. And another one is alternating current or AC, okay. And of course, AC could be like, it could be alternating, means it moves up and down, it's alternating, right? So therefore, it could be like a sawtooth, triangular, square wave. But since our world use sort of like sinusoidal, so therefore in electrical engineering field, when we talk about AC alternating current, it's always in terms of the sinusoidal waveform, okay. So that's current. Resistance, next one, resistance, okay. Resistance R, okay. Well, resistance, and we call that, well, it's the resistors that provide you with resistance values. The symbol is this symbol, okay, for R, right? Unit is ohms, right? Unit is ohms, okay. Well, resistance is there such that it will limit the flow of electrical current, okay. It restrict the flow depending on the materials you're using to make these resistors, okay. Well, we want to be able to control the current. We don't want everything to go freely. We have to be able to control it. Like, I want current to go in this direction this much, into that direction that much. So therefore, resistance come into handy to like restrict the flow of current, okay. As the name call, resistance, okay. It resists the flow of current, okay. Resistors, okay, come in like color code, okay. So color code like this, right? You would have the material looks like beige color and different color stripes. There's like a 4 or 5 bands, okay. You can go and look in Google image, like, type in Google resistors, resistance, and look at the pictures of what it's like. There's so many type of it. The simple one is, of course, the fixed resistors. And the simple one is 4 bands, okay. So these bands are sort of like look like this, okay. Well, the bands coordinate with certain values. Well, there would be the three colors that sort of like close to each other, and then some space, and there's another color at the end, okay. Well, the one that's far away from the other one out of the pack is the tolerance. That would be 5% if it's gold, okay. If it's silver, it's 10%. If it's no band, it's 20%, okay. Well, then you look at the first band, okay. It's called the first digit. The second one is the second digit, and the last one is the multiplier, okay, multiplier. So the colors, well, of course, if you have a multimeters to measure the ohms, then you can use it. If you don't, and you want to just like, if you have a pile of resistors and you want to guess, sort of like guess what their values are, you have to be able to remember the color, the value that's associated with the colors, okay. So the way I remember this is, of course, I'm sorry, it would be bad boy, okay. Bad boy robbed our young girl, but Violet gave in willingly, okay. So the first B with BA, so associated with black, okay. Boy, okay, with O, so brown, okay. R for red, O for orange, Y for yellow, G for green, B for blue, V for violet or purple, gray, G for gray, and W for white. And the numbers are 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so therefore, if you have the color red, black, red, okay, red, black, red. So you go to red, right? Red is 2. So this is 2. Black is 0. Right, 0, and 2 is red is 2 again, so times 10 to the 2, because the last one is the multiplier to the power of 10. So therefore you have 20 times 10 to the 2, so it's 2000 or equal to 2k ohms, okay. So equal to 2k ohms, right. So if you get your color sort of like, in your embedded in your brain, you will sort of can guess what the value of your resistors is. Okay, so if you have violet, red, orange, for example, you have violet, red, orange, right, like this, right? So you would have violet is 7, right? Red is 2, orange is, that's orange? 3, so times 10 to the 3. So this is 72k ohms. Okay, so as simple as that. If you do a lab, I'm not so sure whether you have a sort of like a lab for testing your skill in the color code or not. Okay, so that's about resistors. Okay, next one, conductance, G, capital G. It's just something that we define as 1 over R. It's a conductance, and the unit is Siemens. Okay, I remember when I went to school long ago. Okay, I remember the conductance was Mohs. We call it Mohs. It's just like upside down omega. But no, I suppose it's out of date. So now it's Siemens. Okay, so therefore, that's conductance. Next concept, ground. We have heard about ground, right? Grounding, okay, 0, okay. You put everything to ground. You don't want to be shocked or be electrocuted, so you have to put your appliance to ground, okay. So grounding, okay. So in electrical circuit, well, we're not really strict about the symbols, but we should know that there are different type of symbols for grounding, okay. So if you have this one, it's called the earth ground. As it said, earth ground. So you stick the copper rod or something into the earth. Okay, so earth ground. Next one is chassis ground or circuit ground. Okay, it looks like this. Okay, chassis ground, as it said, chassis like a case, right? If you go and look in your car, for example, your car is full of electrical wires, electrical systems, right? Where's the ground? Do we put it like what? It's like your tire, a grounding place, because it's like stick to the ground. Well, I don't think so, right? So actually, if you look in the some of the cars, you can see it clearly, like old style car. You see that there would be a place that like there's a metal rod connected from the your engines in your compartment, and it would stick into the body of the car. Okay, that's chassis ground. Okay, so you try to go and have a look, open the hood of your trunk of the car and see if you can find chassis ground, okay, for all our electrical circuit in the car. Okay, another one is of course signal ground. Okay, signal ground. Okay, but all of this, okay, all of this, it just means that grounding is a reference point. It's a reference point, okay? Ground is a reference point and has a potential of 0 volt with respect to other point in the circuit. Okay, this is the definition of the word grounding. Okay, but anyway, you see a lot that we use earth ground a lot. It's simple to write, so that. Now next, basic circuit. Okay, basic circuit. Okay, basic circuit consists of 4 items, 4 components. Okay, first one is the source. Okay, source. Okay, could be current source, voltage source. Okay, the battery is considered a source. Okay, there's a switch. Okay, switch. Okay, there's of course your electrical appliance or your load. This is like a lamp. Okay, load, and of course you need a wire for your current to flow. Okay, so your source, your path, the wire, your load, and of course I forgot here the switch. Okay, to open and close the circuit. When you have a complete circuit, so switch falls down here, right? The switch falls down. okay, long line for positive, short line for negative, okay. Current can flow. Current needs a complete path to flow through, okay. Then of course the light would shine, okay, turn on and shine when the current passing through, the lamp, okay. So this is a simple basic circuit, the components of it, okay. When the switch is closed, right, I say, okay, the switch is closed, well, we call it a closed circuit, okay. And when it's open like this, right, when it's open like this, when the switch is open, okay, there's no complete path, so therefore current cannot flow through, okay. Current cannot flow through, it's broken, the path is broken. It's called an open circuit, okay. So I say here, so this is closed circuit, right, complete path for the current to flow, open circuit, okay. The circuit is opened, okay. But the current would flows when there's a complete path. So for example, if this is if I'm a current coming out from the source, okay, it would flow through the wire that allow it to flow. So it would go like this. If the switch move to the position 2, right, the current would flow just simply here, okay, and no current go through this one, okay. So you need a complete path. Now let's look one by one. Source, okay, source. Now go to the source, this one right here, okay. Now sources, there are sort of like two types, two major types, categories, called the dependent and independent types, okay. And in each one it also has the voltage source and current source. So in this case we're going to learn how many, okay, let's see. Let's look at independent first. Independent voltage source. So we would have like this. We would have, this is the source, right, source. We would have independent, and we have dependent, okay. And independent, there's also voltage source and there's a current source, okay. For dependent also there's a voltage source and current source, okay. Independent, okay, like here, okay. It means that no matter what is connected to your source, the voltage will give you that values. If we said Vs is equal to 5 volt, it will always give you 5 volt, okay. They would induce a current such that it would keep 5 volt, and the symbol is, it could be this, right, circle with positive or negative inside, or this long and short lines where long line is a positive and the short line is negative, okay. And if AC, sometimes you hear this, you see this so-called sinusoidal wave inside the circle, okay. This is independent voltage source, okay. If it's a current source, okay, it's a circle with the arrow telling you the direction of the current. So that's a current source. So if a current source, you have current source, independent current source, it said, okay, 3 amps. Then no matter what circuit you're connected to it, okay, it will always give you 3 amps out of that source, okay. Now what about dependent source? Dependent, right? Dependent means you depend on someone else, okay. You need someone else to give you the values, okay. The symbol of the dependent is the diamond. For the voltage source is a diamond with positive and negative inside, okay. Well, and then who controls it? Who has a control depending on whom, okay. So there's two parameters that can control it, okay. It can be controlled by another voltage source in the circuit. So therefore you would have, it could be AVX, okay. This VS could be AVX. So it's called the, okay, voltage control voltage source. If it's controlled by the current somewhere in the circuit, Ix, it is called the current control voltage source. It's a voltage source, but it's controlled by either voltage or the current. Okay, the symbol to show that it's a voltage source is positive or negative inside the diamond shape. Okay, is it voltage control or current control? It depends on whether this is a Vx or Ix. Okay, so this is this case here. Oh, sorry. This is this case, right? It could be Vs equal to AVx. This is a voltage control voltage source. Or it could be Vs equal to AIx. It's a current control voltage source. If it's dependent current source, it's also a diamond shape like this. But you know that it's current because there's an arrow inside telling you the direction of the current flowing. Okay. Well, it can also be controlled. It depends on the other materials. If it's depend on another voltage in the circuit, it's called the voltage control current source. Right? So it would be, well, Is would be equal to AVx. Okay? Or it could be controlled by another current in the circuit. So it will be called the current control current source. Right? So you know that it's a current source because of the arrow inside the diamond shape symbol. You know it's voltage controlled by this Vx, and you know that if it's also current controlled by this Ix. Okay, so there are 4 types of the dependent sources. Okay, voltage control voltage source, current control voltage source, voltage control current source, current control current source. Okay, if you have this in a problem, well, the problem is slightly more difficult. Okay, you have this dependent source in your circuit. Okay, next one, energy and power. Okay, energy and power. Okay, 2 terms. Okay, well, energy. How do you know something? Energy is generated. If you imagine that you turn on a light bulb. Okay, you turn on the light bulb. Okay, and you turn it on, right? Give it a few minutes, and then you touch it. Okay, the light bulb will be hot. Okay, that tells you that, well, there's some energy released. Okay, in terms of heat. Okay, somehow there's energy has been generated. Okay, well, that's energy. Well, let's look at and then what is power then? Okay, well, power is a measure of how fast energy is being used. Okay, how fast energy is being used. Okay, and the so-called formula is P equal to energy per time, because it's how fast, like the rate of energy is being used. Okay, and the unit is watt. Okay, that's like work energy per time. Okay, well, in electric bill. Okay, well, energy is like joules, right? But in electric bills, we sort of like make it that we understand it very clearly. So, for example, if you are studying for my class, okay, and your lamp by your working table, your study table, you turn on a 100-watt light bulb, and you study so hard for my exam, okay, for 10 hours. Okay, So we say that, well, if you multiply 100 watt for 10 hours, 100 watt for 10 hours, you get 1000 watt hour of energy. So you're using 1k watt hour of energy. When you're doing that, you turn on a 100 watt light bulb for 10 hours. Okay, so we understand, we sort of like make it easier to understand. Okay, and of course in Thailand, okay, you are being charged for the energy you are using. Okay, so therefore in Thailand it's like 1 unit. We charge the electric bill using a unit. 1 kilowatt hour is equivalent to 1 unit. Okay, so now you go back, if you live in a dorm, you can go and ask, how much, your dorm charge your electricity, okay, for 1 unit. Okay, and as in for, so power, right, back to power. So when you say 1 watt of power, so 1 watt of power, you can think of it as when 1 joules of energy is used in 1 second. Okay, so that's energy and power. How about the power in electrical circuit? Okay, we don't deal with energy, right, power. So I mean in the formula that we remember for power. So what is it is? Well, from here, right, power is energy per time. So P is equal to dW per dt, but it also can be written as dmu dq multiplied by dq dt. Well, this is your definition for voltage, and this is your definition for current I. So therefore, that's why we remember our power formula in electrical class as P equal to V times I. Okay, and of course this V times I, we normally means that, where's V, right? Well, V is the potential difference, okay, of that wherever we want to find, across wherever we want to find that power, and the current I is the current passing through that items, okay, that you want to find the power for. Okay, now power, there is a word that we can say that, are we generating power, or are we consuming power? Okay, true. And the way we define this, okay, it's like this. You look at the direction of current flows. Okay, so for example, you have this source, okay, and you have power, you have circuits, you have current flowing out of the positive terminal of the source, right, Vs. Okay, so if you have power, if you multiply, you want to find power for this voltage source. You want to find power for this voltage source, right? Okay, if I say that Vs is equal to 5 volt, I is equal to 3 amps. Okay, then if I say, well, P is equal to V times I equal to 5 times 3 equal to 15 watt. Okay, the answer is positive values. Okay, in this case, when the current flow out of the positive terminal of that source, of that items that you are calculating, and it turned out to be positive, we say that the power is generated by that thing. So in this case, by Vs. Okay, but somehow, if your I is negative 3 amps. Okay, so then it's P equal to 5 volt times minus 3 amp. The answer is minus 15 watt. Okay, we say that, well, your answer is negative, and it's this so-called direction of current. We say that the source consume 15 watt. Okay, the negative sign indicates that this source now is consuming the power. Okay, right? What about if you have another way around? If you have a current entering the positive, see this one above here, currents leaving the positive, right? But in this case, currents entering the positive. Okay, and if said, well, okay, V is equal to 5 again, volt, I equal to 3 amps. So I said P then equal to 5 volt times 3 amps equal to 15 watt. Answer is positive. But in this case, when you have a positive answer, we say that the power is consumed by this load, 15 watt. 15 watt of power is consumed by this load. If I have, let's say V equal to minus 5, then P is equal to minus 5 volt times 3 minus 15 watt. The answer is negative. It falls into these categories right here. It means that I have to write that, well, this load, this so-called square thing, no, rectangular thing, load, okay, generate 15 watt. So therefore, to say it's either going to be consuming or supplying or generating, okay, you have to look also at the direction of the current flows, okay. So please be careful, okay, because this is a passive sign convention, okay, passive sign convention, okay, all right. So this is the example I just did it right now, okay. So, well, this is the end of the first lectures, the first sessions. So therefore, if you want to go back, so you can go and repeat the course again and write onto your lecture note, your own lecture notes. Okay, so I see you in next sessions. Thank you. Bye.